All right, good afternoon, everyone. Let's get started. So we're talking about transport layer, right? This is what we started last time. I think we got through maybe a couple of slides. We basically discussed multiplexing and demultiplexing. This is a function or service that's implemented at the transport layer, but actually doesn't really have to do with end-to-end reliability. Remember, end-to-end reliability is the main task of the transport layer, and this is a function that's implemented there, but not really connected to end-to-end reliability. And the main idea here is that the transport layer provides a connection between processes, and because all these processes live on the same interface, you need to find a way to address them. And we address them through the idea of a port number. Right? And so the first 32 bits of every transport layer packet, the first 16 bits is a source port, the next 16 bits is the destination port, which is the next hop. It's the MAC address of the next hop. It's the port number. Apologies, this is not MAC. This is the source port and destination port is end-to-end. The source and final destination. Okay? And then we also looked at UDP. UDP, User Datagram Protocol, is a transport layer protocol that does not deal with anything that's related to reliability. Okay, and so all it really has is the source port, destination port, and it happens to have a checksum and a length of the header. Okay, and but beyond that, there's nothing else. Okay, and then we talked about why would you use UDP? You'd use UDP when you want to have, when you don't need reliability and you want to have finer control of timing. Do you have a question? No? Okay. So you want to have finer control over timing. Okay, TCP you have slightly less control over when the packet is sent out. So real-time applications, but as I ended with last time, most modern applications use TCP. And they work fine in real time, right? Skype, Facebook, WhatsApp, all have a TCP version, and they work fine, right? So this tells you the network is getting really very good, right? Our network is becoming very stable and somewhat reliable. But, there are still real-time applications out there that use UDP and other applications like DNS that don't require reliability. So they use UDP instead of TCP. Okay, so this is where we ended, and now we're going to talk about TCP, which is the transport layer protocol that captures end-to-end reliability. Okay, it has a variety of mechanisms for end-to-end reliability. So, for example, it's connection-oriented. We'll see that it sets up a connection. It deals with things in terms of bytes. It sequences every byte so that you can figure out. So you can figure out if packets have been lost or not, right? And you can put them in order. Okay, it has acknowledgements, so that you can do retransmissions if packets are lost or if packets are corrupted. Okay, and finally it has flow control. It has flow control and congestion control. Both flow control and congestion control are mechanisms to determine how much data the sender pumps into the network. Right, and you can see that's related to reliability because if the network is not doing too well, you pump less in. If the network is doing well, you can pump more in. All right, so these are all the mechanisms that we're going to talk about. But before we do that, let me give you an analogy of talking on a cell phone, right? So let me see, Benita, right? Let's say we're on the phone and we're talking, and you're telling me a story, like about how your prof is annoying and he gives you too much homework and too much work to do, and we're talking. It's not me, obviously, but some other prof. And what am I going to do? Do you think I'm going to just keep quiet? Like, let's say we're having a conversation. What will we do? In fact, what do you do? Okay. Yeah. And if we're talking on the phone, what would I do? Yeah, I would say things like, uh-huh. I would acknowledge you. So you see, in everyday speech, we already do that. Right? So that's, okay, that's not what's shown here. But anyways, acknowledgements are there. Suppose that we're talking and you haven't heard from me in a while. What would you ask? Yeah, like this happens on Zoom a lot, right? Where you're on Zoom and like we're talking and I'm muted, right? If somebody's talking, if they have the camera on, you can see them talking, but right? Hey, yeah, you're muted. Like you would, if you don't hear from somebody in a while. So my wife, I'm on the phone with her, and we get cut off, and I continue talking. I'm like talking, and like minutes later, I'm like, hey, there's no response, right? So then I call her back, and my joke with her is I tell her I said something very profound, and I can't say it again. But my point is that you will wait for a response, you will try to acknowledge, right? So all these things that we do in our everyday conversation, this is exactly what TCP does. So when you look at the mechanisms for TCP, you'll find them very natural. They're not going to be like, oh, this doesn't make any sense. Okay? So this is what I say. So there's acknowledgements from the receiver. Say, yep, I hear you, I got you. There's a timeout. If I don't hear from you for 30 to 50, 30 seconds or a minute, I'm going to say, hey, did the line get cut off? Can you hear me? Right? If there's errors, then I'm going to, like, for example, if we're talking and there's some loud sound or disturbance, I'm going to repeat myself. Right? So all these things are there, and these things that we do in everyday life are exactly what TCP does. Okay, so let's talk about that. Okay, and the point is the channels that we have are just like real life. They can have noise, the packets can be corrupted, the packets can be lost. And this is why we need to have the end-to-end reliability mechanism. Now, our why question 2, which we'll discuss at a later point, but I want it in your head, I want you thinking. So let's say that we have, okay, I'll stop picking on students. We'll just say, let's say we have sender, destination, and I'm the intermediate hop. Okay, so the packet goes there, from the sender to me, the relay to the destination. Now, the job of link layer is what? Is reliability. Is to create a reliable link from here to me. Right? And you talked about mechanisms for reliability. You talked about ARQ, right? You talked about retransmissions. But the scope of that is only from this hop to me. And then my link layer and the destination's link layer, that's the job to create that reliable link. Remember, the job of the link layer is to create reliable links. So now, the question I want you to think is, if this link is reliable, and this link is reliable, why is the link, it's a logical link from the sender to destination. Why is that not reliable? Why do we have end-to-end reliability? You see the question? Transport layer is about end-to-end reliability between the sender and destination, not caring about the middle of the network. But if the layer 2 already gives me reliable hop here and a reliable hop here, my second why question is, why do we have end-to-end reliability? Okay, so you can ponder that. Hopefully when we finally talk about it, you have a good answer. Right? Remember, our first why question was also, why do we use MAC and IP addresses? Second one is, why do we have reliability at 2 layers? So the same way we did in the first why question, you should ask a series of questions. I give you a hint. What kind of questions? How many reliability mechanisms do you need? Which reliability mechanism do you really want? And does one, do you need both or do you need only one? And then which one is preferred and why? Okay, so that's what I want you to ask, a series of smaller questions. Okay. Okay, so let's talk about transport layer. Okay, So first of all, so the word packet is going to be generic. Okay, when we say network packet. But at each of the layers, that object has a name. So let's see if you remember. What is the link layer object called? What's a link layer packet called? It's called the frame. What's a network layer packet called? You don't know yet, but let's see if you can guess. It's not a packet, but a datagram. Transport layer packet is called a segment. Okay, and an application layer packet we call a message. I mean, maybe that's not so standard, but segment, datagram, and frame is for transport, network, and link is pretty standard. Okay? So let's talk about TCP segments. So what TCP does is it takes data and it breaks up into bytes. And it essentially sequences every byte. Okay? And its goal is basically, it thinks of just transmitting bytes from the source to destination. Right? And what it's going to do is it's going to build a segment. You can think of it as a boat. You know how, like, if you go to, so I ran into this last December when I wanted to go to Pulau Ubin. And Pulau Ubin, you have the boats there, and they won't go unless there's like 12 people, right? You can be 5 of you, but yeah, if you're willing to pay more, they'll take you. But otherwise, you have to wait for the boat to fill up, then it will go. TCP segment is the same way. It's going to wait until you fill the segment, and then it's going to send the segment. Okay? It's going to send the segment when the segment is full. And there's a parameter called maximum segment size, MSS. That's the size of the segment. And it will wait until it's full. Now, it's not going to wait forever. At some point, it will time out and just send it. This is what I meant that TCP doesn't give you fine control over timing. UDP, a packet comes, if it blasts it out. Second packet comes, it blasts it out. It doesn't wait. Okay, TCP waits. Okay, so here's what a TCP segment looks like. So a TCP segment, because remember, data comes down the stack. So the application, there's a message, there's a header, transport layer adds its own header, right? And that gives you the segment. And that segment is going to then be processed by the network layer, which will add a header. So the segment, the TCP segment, sits inside the payload of the datagram. Okay? And so typically, at the network layer, you also have a maximum transmission unit, MTU, but this MTU is actually settable by the network operator. So if I control a network, I can set it. When we do network layer, we're going to see that this constraint of maximum transmission unit at the network layer is going to force us to break packets up that are larger. That function is going to be called fragmentation and reassembly. Okay, so network layer can impose this. Transport layer has this maximum segment size, and so on. Okay, so this is just to show you where things fit together. Okay, now I mentioned to you that the transport layer is going to sequence every packet. So what's a obvious way of numbering? What are you going to number the first packet? 0. And second one? And so on, right? That sounds reasonable. And if both the sender, now the sender and destination have to agree, right? Because the receiver, the destination is going to check. I'm going to check, did I get everything? So I have to know they start at 0. Now, that seems reasonable, but for practical reasons, we don't do that. All right? We don't set the sequence number of the first byte to 0 or 1. Okay? We set it to something called initial sequence number. It's almost like a random quantity chosen by the sender. Okay? Now, the reason we do that is we'll see that this TCP connection, right, has a lifetime. So if I want to send, for example, Weda, if I want to send you a bunch of packets, I'll set up a connection, and then I will tear down the connection. And if a little bit later I want to send you a new set of data, I'll set up a new connection. So you see you're going to have many connections. We call these connections flows. I'm going to have many flows. Now think about it. If every flow started at 0, there's a possibility that, for example, the first flow, some packet got delayed in the network. It got delayed by, let's say, a second. And in network time, a second is almost infinity. The second flow started is sending packets. Now, at some point, that packet that got delayed, let's call it packet 7, shows up. Oh, wait, is it packet 7 from the old flow or the new flow? Because of that reason, we don't want to start at something like 0. Okay, what the sender does is it picks a random number. And then, but now, since the sender and receiver have to agree, they have to exchange sequence numbers. And that's the connection setup. Okay, so this is so the sequence number here is like for the destination to figure out if it lost packets, if packets come out of order. By the way, why can packets, if the sender sends, let's say 0, 1, 2, 3, 4, 5, why might packets come out of order? Anybody know? Anybody can tell me why? It sounds like if the sender sends 1, 2, 3, receiver should receive 1, 2, 3. Yeah, Benita? Yeah, because the network, and specifically routing, is kind of a stochastic process. You're not guaranteed that every packet will take the same route. Okay, because this is not a circuit switch network. This is a packet switch network. Resources get assigned on demand. Right? So packets may take different routes. They may come out of order. Okay, so the receiver needs to put them back into order. So that's what the sequence numbers are used for. And they're also used to determine if packets get lost. So why might a packet get lost? Why, if I'm sending 1, 2, 3, why might the receiver only receive 1 and 3? Anybody know? Where are packets lost? Is there like a packet monster in the network that eats packets? Why do you think? Why do packets get lost? If you don't know, say, I don't know. It's okay. What? There's a set number. Yeah, at the network layer, there is something called time to live, but the time to live is very big. It's essentially the diameter of the network. So you're likely, unless you're in a routing loop, you're not going to hit that constraint. But that's good. Do you know? Where can packets get lost, or how packets get lost? You're right, but what does that mean? So you're right. Actually, if we both agreed on if I was confident you knew what congestion was, I could accept that. But tell me, what do you mean? Yeah, you're on the right track, but I want to see the mechanism where packets get lost. Convince me you understand. Yeah, what's your name? What? Prince. Not a Z. C. So what Prince said, can you build off that? He said something about buffer getting full. Yeah, so, and I think, Max, you wanted to say something? Yeah. Yeah, remember these routers that we use, or these devices, are what's called store and forward. They have a queue, they take packets in, and at the head of the queue, they're serving their first in, first out queues. And so they're serving, and it takes a random amount of time to serve it. Depends on the packet length, transmission speed, and all that good stuff. And so packets have to queue. And as they're queuing in the router buffer, they can fill up. And if it fills up too much because of congestion, packets can get dropped. Okay, so if a packet gets dropped, the receiver needs to know that. I didn't receive this packet. And it needs to tell the sender so sender can resend it. That's what sequence numbers are used for. Okay, but as I was arguing, you don't want to set a fixed sequence number. Right, and I already explained why. We want to set a random sequence number. And the setting up the usage of random sequence number requires the nodes to communicate before they start a data transfer, right? Now, keep in mind that every connection is two-way because, like, I make a request to, let's say, YouTube, and YouTube is going to send me data. So you might think it's a one-way data exchange, but it's not because I have to acknowledge. So actually, every connection is a two-way exchange. So both parties set sequence numbers, and they have to be exchanged, right? And that's what this is here. TCP uses a three-way exchange. Okay, there's a SYN, SYNAC, and ACK before data is sent. So let's look at the TCP header. Okay, so this is the anatomy of a TCP header. This is the first time, I guess, that we are seeing this. So maybe we take a moment here. So again, the first 32 bits are the source and destination port. Now in TCP, the next 16 bits are sequence number. The next 16 bits are acknowledgement. And then we'll see what the acknowledgement is in a minute. Then there's other flags, header length flags. Some flags that are going to be used to do that three-way exchange. Then you have advertised window. The advertised window is to do flow control. Okay? Then there's checksum. This is the error detection code. And then some other optional variables. Okay? All right. So and then the payload. Okay? So remember, I have SYN, SYNAC, and ACK. Okay. So let's look at those. When A who wants to initiate the connection sends a SYN packet, A is gonna set the source port to be its port number, the process that generated that packet, that request. The destination port will be B's port number, meaning the process that it wants to communicate to, like the web server, might be port 80. Then A will put its initial sequence number, whatever it chose. Okay, and then it's going to set this SYN flag to show this is the initial connection. Okay, then B is going to respond. Once B gets that, B will respond. It's always going to swap the source and destination port, right? Because it's now the source. Okay, it's going to now set its initial sequence number. And it's going to put an acknowledgement, but let's not worry about that for a minute. This is kind of the acknowledgement happens to be a sequence number plus 1. We'll see later that this way of acknowledging, it's not acknowledging if I received or did not receive a packet. It's telling the other party what packet I'm expecting next. Right? So it turns out that's the equivalent way of acknowledging, and that way has advantages in terms of acknowledgements accumulating. Okay, so it has a little bit of an advantage. But anyway, there's an acknowledgement, and then it's going to set the SYN and the ACK bits. And then finally, A will respond and say, oh, I got your sequence number, and it will set the ACK bit. That's the three-way handshake, and then data can start flowing. Okay? So TCP is connection-oriented. It sets up this three-way handshake, and in the handshake, it's exchanging sequence numbers. Okay? So again, when I thought about this, I realized it connects to a behavior that I noticed. So maybe I don't let you look at that. I don't want you reading. I want you listening to me. Okay? So who has had this experience where when you click on a link and then you wait, and it's the browser icon is spinning, and then you get kind of you get impatient, so you click the link again, and it works the second time, right? So what happened? Why was it just taking a long time? Well, probably what happened is that first SYN packet was lost. Now, if your SYN packet is lost, there's nothing the destination can do, right? It's not going to respond. What? You never contacted it. Yeah. So that's what happened. So when you click the link again, you're just preempting that. Now, now you might ask, why don't I time out? Well, remember, initially, when I'm trying to contact a destination, I have no idea where the destination is. I have no idea of the expected round trip time. Right? So usually you set your timer to be like 5 seconds. And actually, 5 seconds is very long. It doesn't sound like it, but I'm going to prove it to you. I'm going to keep quiet for 5 seconds, okay? That's crazy, right? You're like, what is this crazy guy doing, right? Why is he not talking for 5 seconds? I just want to tell you, from a human behavioral point of view, we are very impatient. So that's why we're always like clicking, you know? But actually, it turns out it's a good thing to click. It's very different from the traffic light. You know, the traffic lights where you cross and you walk up and you're like, I see people go up to that and they just keep pressing that thing. And I want to tell them it's not going to work because it's already pressed. But maybe, who knows? Maybe I'm the one who's wrong. Maybe pressing it makes it turn faster. Yeah, so this is what I think. So I like to find connections to things that happen in my daily life. So that's what I'm trying to explain here. Okay, this is like the sin packet. It's like you've interacted with it unknowingly. Okay, and then I think this is just talking more about the sin packet. Okay, and then so TCP, because it's connection oriented, it constructs a connection. It has to tear that down. Okay, and the tear down here is actually it's a four-way connection: fin, finac, fin-ac. An interesting question, which I'm not going to address now, but you guys can think about, is why is this four-way? Right? Why is, for example, 2 not enough, or 3? Why do we have a four-way teardown? Okay, but it's something to think about. All right, but the point here is that TCP is connection-oriented. Okay, you set up and you tear down. Okay, so that's sort of one idea here. The second idea, which is very much tied to reliability, has to do with retransmissions. Now, you already talked about retransmissions. You already talked about ARQ. Am I correct? So while the material is here, I'm not going to dwell on it. But you know by now that, for example, stop and wait is very inefficient. Right? So for example, what's the throughput of stop and wait? Does anyone remember? So let's say I'm a sender, and I send a packet, and then I wait for a response. And I only send my next packet once I get the response. What's the throughput? Or what's the rate at which I can send packets successfully? Well, there's formulas, so let's not worry about. So there's transmission time, right? There's all that stuff. Let's ignore all that. What matters to us is what? There's one thing that matters at the transport layer. What is it? It's the round trip time. Why? Because the round trip time is over all the hops, whereas your other things are like much smaller because they depend on the local link rate and the size of the packet. And it turns out that that's going to be much smaller than the actual round trip time, which is that delay across all the nodes. Okay, so typically at the transport layer, we're going to ignore the things that you looked at the link layer because they're much smaller. They're dominated by the RTT. So what's the throughput of stop and wait? 1 over RTT, right? Because every RTT, you send one packet. Right? Simple, right? So, and that's inefficient. As RTT gets large, this thing goes to 0. Okay? So it's very inefficient. What's the solution? Do you guys, what was your solution for stop and wait being inefficient? Yeah, you use a sliding window. A window meaning I allow a bunch of packets to be sent unacknowledged. Then as soon as I receive one acknowledgement, I send the next packet. So I slide that window down. And that's what TCP uses. TCP uses sliding window. But before we get to a sliding window, and I think you've also seen these diagrams, right? Where you have a sender, receiver, and you have a packet and an ACK, right? So this is, so again, I'm abstracting the middle of the network. Okay? This is not 2 nodes next to each other. This is 2 nodes separated. But I don't care about the middle because TCP or the transport layer is end to end. Okay, so these are the kind of diagrams I want to use to illustrate a couple of points. Okay, I want to illustrate 3 points. Okay, I realize that what it shows me here is not what it shows me here. It shows me everything. Okay, so I got to remember that because there's animations here. Okay, so let's talk about this. So let's say I have a situation where a packet gets lost, right? And remember, there's this idea of timeout, meaning that there's a so remember in the SYN packet I said we set a so timeout is the time I wait for some response from the other side. Okay, if I don't hear a response past that, I'm going to assume something has gone wrong, right? It makes sense, right? Like if you're on the phone, after 30 seconds of no contact from your other side, you're going to think something has gone wrong. So, and for the SYN packet, we set that timeout to be very long because we have no idea what the expected timeout should be, right? So, what we'll see is that for TCP, one of the major functions of TCP is to estimate that timeout. Okay, we're going to estimate the round trip time and use it to set the timeout. So let's look at it here. So I have a packet that A sends. So the left is always the sender. The right is always the destination. Let's say that packet gets lost. Now, at this point, the destination is not going to respond. It didn't get the packet, right? So what's going to happen is the sender is going to wait. It's going to wait for a response, and it's not going to get a response, and it's going to time out. So let's assume it set some timer. Okay? For the moment, forget how it set it. It set a timer. The timer is going to expire, and the sender will resend the packet because it's going to assume something went wrong. It's going to send the packet, and then it got an ACK, and everything's good. So this is what I call packet loss. And in this instance, you actually want to resend the packet because the first packet got lost. All right? We'll leave the timeout for a minute, assuming I set a timeout. Okay, second scenario, the ACK gets lost. The packet gets through, but the ACK gets lost. Now, if the ACK gets lost, again, the sender is still going to time out. But now, it's going to resend the packet, but notice that this packet is actually unnecessary. But the sender cannot know. So it's forced to send it, but it's a duplicate packet. Okay, and then it will get the ACK, and all is good. And then the third scenario is that the packet the ACK got delayed. If the ACK got delayed, the sender will still time out. So now we see setting the timeout is very important, right? Because sometimes you do want to time out, and sometimes you don't want to time out, right? So here, the ACK got delayed, the sender timed out, sender will retransmit. This is another duplicate packet scenario. The sender will send another packet, and it will now get the original ACK plus the new ACK. Okay? So it's these kind of situations that TCP has to deal with. All right? And TCP has a mechanism for doing this. Now, let's see, let's talk a little bit about this timeout. So it would turn out that setting this timeout is very, very important. Because if your timeout is too long, then what happens? In scenario 1, my delay is very long. Because in scenario 1, up here on the left, you really want to retransmit. But if your timeout is too long, you're going to have a very long delay. Okay? Now, the same thing in scenario 2, you also, in some sense, have to retransmit. But in scenario 3, you don't. So if your timeout, so this is if your timeout is too long, these suffer. If your timeout is too short, this suffers. So setting the timeout is very, very important. Okay? And so if it's too short, you get wasted retransmissions. If it's too long, you get excessive delays. So now, it's very clear this timeout should be a function of the round trip time, right? So tell me, this is a question for you. Is timeout the timer, by timeout I mean the timer that you set, is it inversely proportional to RTT or is it directly proportional? So who says it's inversely proportional? Who says it's directly proportional? Yeah, so many people are saying that directly, but some of you don't know. Like, you didn't raise your hand. What? Okay, so tell me. Okay, so let's talk about it. So let's say, okay, I like pizza. Let's say I send you off for pizza. Okay, to go to Holland Village for pizza. How long do you think I'm going to wait until I am worried about you? How long? Like what will it depend on? Yeah. Right? Well, it would depend on how long it takes you to get there and come back. So now, is my timeout inversely proportional to round trip time or directly proportional? It's directly, right? So, yeah. So TCP is going to set the timeout as a function of RTT. And what it's going to do, it's going to put some fudge factor because network is dynamic and stochastic. So it could, for example, measure a timeout, right? It's going to send a packet out. It starts a counter. The response comes back. It can measure a round trip time. It can now say, oh, for the next packet, I'm going to set the timeout as like maybe, I don't know, 2 times RTT or something, okay? But the network is changing very, very fast, and you don't necessarily want your timeout to keep chasing the network, right? So what we end up doing is we come up with like let's call it a moving average. We're going to so call this estimate 1, okay? My estimate 1, which I call the smooth estimate, is just a running average of the RTT. So my estimated RTT is my old estimate times A plus 1 minus A times my current measurement, my current estimate. Okay, and you get to choose A. If you choose A to be 1, then you just have a historical estimate. If you choose A to be 0, then you're just chasing the current estimate, okay? And then you set the timeout to be something like 2 times the estimated RTT, okay? But this is, call this version 1. Don't worry so much about how timeout is set. I want you to get into your head that setting the timeout is important. And a lot of TCP research is centered around choosing the right value of timeout. Okay, so here's an example of an actual trace. This is taken from that book by Kuros and Ross. Okay, and the blue is the sample RTT, and the red or the maroon or pink, I don't know what color that is the running average, right? So you can see that the running average kind of tracks, but it doesn't fluctuate a lot. Actual network dynamics can fluctuate, yeah? That's a good question. So you say, yeah, acknowledgements are cumulative, but the destination does not exploit that. It doesn't wait for 6 packets to come and then send a cumulative acknowledgement. For every packet it receives, it's going to send an acknowledgement. Does that make sense? Yeah, so you will be able to tie, hopefully, and we'll see. This is one of the challenges with doing this smooth estimate, right? Is when an acknowledgement comes back, which transmission do you tie it to? Yeah, so that's probably my next question, right? So again, you have to tell everybody I didn't pay you because your question is actually answered on the next slide. Okay, so the approach that estimate 1 says every packet I send, I'm going to try to compute an estimate. Okay, the flaw in this approach is that it's difficult to know when I get an acknowledgement which transmission to tie it to, because I have to tie it to a transmission because the difference is the RTT, right? So for example, if you have retransmitted a lost packet, right? If you tie the acknowledgement to the first transmission, your RTT is too long, right? But if you have a duplicate packet and you tie it to the second transmission, your RTT is too small. Okay, so yeah, so because of that, one solution is to only compute RTT from packet sent once. Okay, and that's a version of something called the Karn partridge algorithm. Okay, so this is still the smooth average, but you only use packet sent once. Okay, so if you look at this here, you see that the variance of the sample RTT is much higher than the smooth average. So essentially, this estimated RTT, when it's a smooth average, is essentially a low-pass filter, right? This moving average is equivalent to a low-pass filter. And so it's taking all the high-frequency movements, and it's cutting them out. So we see that the estimated RTT is missing something here. And so another approach to this, which is shown here, is the Jacobson-Carrel's approach, is to take your estimate and boost it by something that depends on the variance of your sample RTT. Okay, again, these are all a bit ad hoc, but it's trying to fix any problems in the previous estimates. But again, this is not a class in determining round-trip time. I just want to tell you that this is an important thing that TCP has to do. TCP needs to do it right, and there's a lot of research into getting the right estimate of round-trip time. Okay, everybody good? Yeah, all right. Okay, so that's about retransmissions. Again, I didn't dwell on it too much because the idea of ARQ you already know. Okay, and I think my next thing is about a sliding window, so maybe we'll end with this. So because stop and wait is inefficient, we're going to use sliding window. And the idea of sliding window is that I allow a batch of packets to be transmitted unacknowledged. But then I stop. So let's say my transmit window is W. So I send W packets, but then I wait. And as soon as I get an acknowledgement, I send W plus 1 packet, and so on. And then I just keep sliding down. So what's the throughput now? Roughly. Assuming RTT is much bigger than like transmit times. Yeah, it's W over RTT. Exactly. And that would turn out to be our first estimate of the throughput of TCP. Why? Because W over RTT is actually the sending rate. Right? It's actually the rate at which a transmitter or the sender is sending. And clearly, you can't receive more than the sender is sending. So the sending rate is an upper bound on the actual throughput. But it's very, very easy, W over RTT. And so it captures the trend. It tells you that the throughput is inversely proportional to W, to RTT, and directly proportional to W. So it captures all the trend. So it's going to be our sort of go-to estimate to try to figure out what's going on. Okay? So that's sliding window here. And now this window size, right, is something that's determined by the transmitter. Because the transmitter is sending data. So the transmitter has a transmit window size. It turns out this transmit window size is controlled by two mechanisms. The first mechanism is the destination telling the sender, hey, I'm busy, please don't send me a window size greater than something. And that's the advertised window field. Remember I told you in the TCP header, let me see if I can find it, there's the advertised window field. Right, so this advertised window field is the destination telling the sender, this is your maximum window size. This is called flow control. It's the sender being considerate of the destination. Okay, flow control is the sender being nice to the destination. Okay, the second mechanism that TCP uses to control the transmit window size is congestion control. Congestion control also adjusts the window size, but there we're trying to be nice to the rest of the network, the nodes in the middle. Okay, and we'll see when we do congestion control, the sender has to infer congestion is happening, and when it infers congestion is happening, it's going to adjust its window size. Now, the transmit window will be the minimum of the congestion window and the advertised window, the flow window. Right? It would take those two. Now, typically, the flow window is not the tighter constraint. The congestion window is the tighter constraint. So typically, we just say the performance of TCP is determined by the congestion window. But actually, keep in mind that it's actually the minimum of the congestion and flow windows. All right, so I think that's pretty much all I want to say. I think it's a good time to stop. I think, yeah. Okay, because when we come back on Monday, we'll start talking about fast retransmission and recovery, and then congestion control. Okay? All right, good. See you guys on Monday.